Just like when we did reactions in grade 11, organic reactions can be divided in different categories based on our reactants and products, particularly the reactants. Okay, so we can have addition and elimination reactions. These are basically the same reactions, just we change our direction. We can have substitution reactions, where we replace something, condensation reactions where we remove water, hydrolysis reactions where we add water, oxidation and reduction, which are opposites of each other as well. And so we tend to put these or clump these together. So a addition reaction. This is where atoms are added to my carbon chain. And usually when we do this, we're breaking a double or triple bond. Okay. And when we break our double or triple bond, then we will add something to each of the carbons that was added in that bond. Now, depending on what we add, that determines the type of reaction. However, the process is the same. So if we add a hydrogen, it's hydrogenation. A halogen, halogenation. A hydrogen halide, hydrohalogenation, or water hydration. Okay, so for example, if I take my ethene or ethyne and I add hydrogen gas, I break my double bond or triple bond, and then I get an alkane or an alkene, as we can see here. Okay, now for this reaction to occur, I need a catalyst, usually platinum, plus we have to do it, add energy in the form of heat, and usually this is done under pressure. Whereas if I want to add a halogen, I can take my alkene and add a halogen, and this reaction does not require a catalyst. Okay, it can be done at room temperature. Now, when we want to add a molecule that is unbalanced, where I'm going to add different things to each of the carbons, then I have to take into account something called Markovnikov's rule. Markovnikov's rule says that the carbon with the most hydrogen is most likely to get the hydrogen. Now I would identify my major product. Basically, to summarize it or make it simpler, the rich get richer. Okay? So, for example, if I do my hydration of water, okay, an alkene, I add it, I'll get an alcohol. And I could get either a primary or secondary alcohol depending on the type of alkene that I have. So for example, if I have my propene, then I have now two carbons involved in my double bond that have different numbers of hydrogen. So this one has one hydrogen and this one has two. And so as a result, when my water breaks up and is added to this, and remember we can think of water as HOH, one of these carbons will get the hydrogen and one of them could get the OH, or it could be the other way around. And since the location of the OH determines the name of the compound and its properties, we could end up with two possible compounds, where my hydroxyl group goes on my carbon 2 or goes on a carbon 1 in a chain. And now, because of Markovnikov's rule, which states that the carbon with the most hydrogen is most likely to get the hydrogen, so therefore this carbon start off with two hydrogens, so it's most likely to get the hydrogen. That would make it my major product. Okay, whereas the carbon with the least number of hydrogens could still get the hydrogen, but that would make it my minor product. And all this major and minor means is that one is more likely to be formed over the other. Likewise, and this reaction, just like many reactions involving water, requires heat and strong acid. Similarly, if I add a hydrogen halide to my reaction, I can have the same thing occur. So for example, again, I take my unbalanced alkene and I'm going to add a hydrogen halide. So in this case, I am adding HCl. So one of these carbons is going to get the chlorine and one of them is going to get the hydrogen. And again, because this carbon has the most hydrogens, it's most likely to get the hydrogen. And that would be my major product. But the other carbon could also get the hydrogen and form my minor product. And this reaction, again, because it involves a halogen, can be done at room temperature. So our elimination reactions can be seen as the reverse of our addition reactions. But when we're removing from a potentially unbalanced, we have the reverse of Markovnikov's rule, which basically just says the carbon with the most hydrogens is least likely to lose the hydrogens. So for example, here in this molecule, this rule would not come into play because the two carbons on either side of this molecule, the carbon that has the bromine, have the same number of hydrogens. So there's no preference. It's balanced. Whereas in this case, this is not balanced. So again, I have my bromine that I could remove. This carbon here has 3 hydrogens, and this one only has 2 hydrogens. So now the 2 carbons on either side of the carbon with the entity that's going to be removed is not balanced, and so I could lose a hydrogen from here or from there. And since the rich stay rich, the hydrogen-rich carbon's most likely to keep its hydrogen, so I'm more likely to lose it from here. Okay? So, for example, and this only comes in play with the removal of a halogen or a hydroxide for us. So, for example, if I have my hydroxide and I'm going to have it undergo an elimination reaction, remember I can lose a hydrogen from here or from here in the process when the OH comes off. Because this carbon has more hydrogens, it's least likely to lose. Since this carbon has fewer numbers of hydrogens, it's more likely to lose. And so as a result, it just determines where my double bond would be. Because if this carbon loses a hydrogen and this one loses a hydrogen, they both need another bond. So I get the double bond between them. Okay? And likewise, the other ones. In a process, again, my hydrogen from one of the carbons combines with hydroxide to give me my water. Okay, we have our major product, our minor product. And again, because this involves water or hydroxide, we need both heat and a strong acid for it to occur. Okay, if I want to remove a halogen, same thing. Okay, where I can get more than one product if my carbons on either side of the carbon with the hydrogens have different numbers of hydrogens. Okay, for a major product, minor product, and this reaction would require a strong base to get the